done by Clifford, which really make it available to most of the readers. But even before that translation was available, all the mathematical world already knew about this paper, which changed the fundamentals of Euclidean geometry. And I flash you the most physically important, in a sense, achievement related to the Riemann formulation of geometry, which is this expression for the Riemann tensor and the Einstein equations, which are the fundamental equations of general relativity. But today I would like to say a few words about the other fundamental achievement by Riemann. That is, and don't be scared with this extremely long expression, for, I mean, it's irrelevant. It's just for those of you who are interested in mathematics, it's a definition of a Riemann function zeta. It's a function of a certain variable s, and that variable can be a complex number. And after defining that function, Riemann had put forward a hypothesis, which is one of those extremely important hypotheses in mathematics, which has not been proven so far. It's one of these millennial problems, and somewhere in a bank there is $1 million award for proving that hypothesis. And I'm absolutely sure that whoever will got that prize will also got the Milner Prize, which is several times larger for the same achievement. And that is a hypothesis which shows up everywhere in the theory of numbers. And the Riemann hypothesis says that all the non-zeros, non-trivial zeros of the Riemann functions are on a critical line, which is a line where the real part of a complex variable s is equal to 1/2. Well, the reason why, I mean, this is absolutely one of the most fundamental hypotheses in the number theory. And as you know, the number theory is one of the most useful branches of mathematics. The safety of our bank deposits and safety of our communication, everything depends on the proper coding of the information sent over the in communication networks, which is not available to those who want to penetrate our discussion. That doesn't mean that there will be any harm done if somebody will listen to our lectures, but if somebody will listen to your transaction with a bank, that's a serious problem. So the Riemann hypothesis is one of those fundamental hypotheses. And what is important is that it deals with something which is called the complex numbers. And as you know from the mathematics, the complex numbers have been essentially introduced into mathematics at the turn of the 18th and 19th century by one of these giants of science, Karl Gauss. Karl Gauss is that individual. About him, there are lots of interesting stories. The one is that when he was a small child, his father, who was a teacher in the Lyceum in Göttingen, took him to the school for, he didn't have any babysitting or something for him. And since he had to go somewhere, he put his son, a little Karl, into a classroom of his colleague who was a mathematics teacher. And it just happened that this mathematics teacher assigned to the students a problem. The problem was to calculate a sum of the arithmetic progression, starting with 1 and ending with 100 So in other words, to sum the addition of all the numbers from 1 to 100. And the teacher was absolutely sure that he will have a completely 1 hour for himself, but that has not happened. But because before he managed to get to his chair from a blackboard on which he wrote the problem, a little Gauss rose his hand and said, "Sir, I do have a solution." So the mathematician came to the little Gauss, looked at the piece of paper on which he scribbled his notes, look at this, and there is this famous statement of that teacher, "Karl, there is nothing else I can teach you." And Gauss was a professor at Göttingen, and he was there already during and after the Napoleon Wars. And after the Napoleon War, a Prince of Hanover, Göttingen is today, it's basically a suburb of Hanover, was his university. And he wanted to have a good map of his possession. And therefore, he wanted to copy the achievement of Napoleon, who makes such a fantastic maps by covering France with the triangles. Triangles is no longer used, but if you, during the summer, walk over the woods, occasionally still, you can find in Poland abandoned giant wooden towers. And this is not obvious reason why they are there, but these were the triangles. The triangles were towers put up in the vertices of triangles, and the whole area was covered with those triangles. And with the measuring the lengths from between each of those vertices, it was possible to generate much better projection of a curved surface of the Earth. Earth is, unfortunately, there are those people who claim that it's flat, but unfortunately it's not flat, it's curved. And if you want to project the curved surface on a plane map, it's again a problem of projection a higher dimension object on a less dimensional space, as we discussed already on the previous lectures. And there are various ways of making that projection very, very well done. So the length on the map corresponds to the real map on a curved surface of the Earth. And Prince of the Hanover, when he decided to do the triangulation and to make a good map, he assigned this job to Karl Gauss. And in order to help him to do this, for he had to build those towers, he assigned him a company of the soldiers who followed the path of Gauss over the county. And the soldiers were needed to convince the farmers that they had to cut the woods and build those towers for a prince, surely without any pay or reimbursement. And since Gauss was traveling and he wanted to know what is happening in science, he and his colleague Weber remained at university in Göttingen. These gentlemen built essentially the first wire telegraph. So Gauss was keeping himself in touch with what is new in science, but during this period of time where he was a commander of I don't know, it was a company or a battalion of those soldiers. And Karl Gauss had created the complex numbers. And as you know, there are essentially and only 4 sets of mathematical objects which have the same property as those numbers we use in everyday life. And these numbers we use in the normal life are called the real numbers. And then the other three sets of fields of numbers are complex numbers, then the numbers which are called the quaternions and the octanions. And out of them, only octanions are not truly applicable in physics or engineering, but the complex number life without the complex numbers and also without the quaternions will be extremely complicated. Quaternions were invented by Irish mathematician, famous mathematician Hamilton. And if you will ever be in Dublin and go over the Brougham Bridge, you might be able still to find some marks on the one of the ramps of the bridge. And the story is that the Hamilton was working madly on how to construct the way of multiplying quaternions. I mean, the numbers have to be also not only added, subtracted, but also multiplied. And the story is that on one of the Sundays, when he was going over that bridge with his family to the church, he all over the sudden got illumination how the quaternions can be multiplied. And since he couldn't scribble any notes, he didn't have a piece of paper or a pen, he used his walking stick to mark the way of multiplying quaternions on that ramp of a bridge. And these hardly visible signs are, it is possibly a city legend that this is the first multiplication of the quaternions. Why I am mentioning that these complex numbers, and the reason is that, as I said, they really have been made available to everybody use at the turn of the 18th and 19th century. And that was a period of a tremendous upheaval in Europe. We had the period of, we have a revolution in France, and after that we had the tremendous number of wars fought by the Napoleon Bonaparte all over the Europe. And one of the most interesting and most fantastic pieces of a world literature dealing with that period of time is a book, War and Peace, written by Lev Tolstoy. This is Lev Tolstoy, and this is a history of the Tsar Russia, which was a friend and enemy of the Napoleon and fought this tremendous war, which basically ended this domination of Napoleon over the Europe. And the book, which is called War and Peace, was written in the 1869. And you might have either read the book or you may have seen the movie. There are various movies based on that book. One of them is with Audrey Hepburn, this famous American actress, playing role of the heroine of the story, Natasha Rostova. The story is about that during the story goes during the time of Napoleon War, and one of the heroes is the Prince Bolkonsky, a young Prince Bolkonsky, who fall in love with the Natasha Rostova, who is a daughter of a very rich merchant from Moscow. She is not aristocratic, and therefore the family of Prince Bolkonsky, particularly his father, old Prince Bolkonsky, he's against this marriage. And at the one stage of the story, Andrei Bolkonsky takes Natasha to visit his father, who the old prince lives in the palace, which is on the countryside. And he's busy with the carpenter. He spends most of his time making furniture and things like this. And there is and the old Bolkonsky has also a daughter, Princess Maria. And there is a discussion between the old prince and those two young girls, ladies, and they both have finished the special schools at the time, the schools for well-born and rich girls. And Bolkonsky tries to show in that discussion that Natasha Rostova is not intellectually au pair to his son. And in that discussion, all over the sudden, the discussion goes on the new scientific discovery of that period. And all over the sudden, Natasha and Princess Maria start to talk about the complex numbers, about the Gauss numbers. And this is, and old Bolkonsky had no knowledge of what are those complex numbers, so he breaks the discussion. And the War and Peace is, as I said, also a base of many movie productions, but there are also the theater, drama theater plays based on that book. And one of the most important adaptation of the War and Peace for a drama theater is then done by this person who is shown here. I forgot to put his name there. The name is Erwin Piscator. He was a German drama director, is just to say too little. He was a person who influenced a change in the drama theater from a purely 19th century into the 20th century theater. He was also a very revolutionary individual, a friend of Bertolt Brecht. Bertolt Brecht, this famous German writer, was the best man on the wedding of Piscator. And Piscator had adapted the War and Peace for Drama Theater, and that is a sign from a Warsaw Powszechny Teatr, which in 1957 had shown the War and Peace in Warsaw using the adaptation of a Piscator. It's here written. And this was incredible performance. And this discussion between the Natasha Rostova and old Bolkonsky about the complex number has been essentially picked up by the Piscator as one of the leads, so to say, of that stage presentation of the War and Peace. Why this is important thing that in the turn of the 18th and 19th century, the girls who were taught in the schools for well-born and rich people, only for the girls, they were taught about the complex number, a discovery, mathematical discovery, which was afresh as a rolls in the morning in the baker's store at that time. And in Poland, almost at the end of the first quarter of the 21st century, we still are not teaching children anything about the complex number. And that is something which I consider to be a subject of reflection for all of us. All right, so that was the digression about the theater. By the way, the Piscator was incredible. He had emigrated from Germany when Hitler came to power, first to Soviet Union, and then quickly he was disillusioned with what is happening there, and he went to United States. He had been one of the directors of the new school of art, and this was a school for drama actors, and the pupils who had finished the school when Piscator was teaching there were so famous drama and movie also actors in the United States, like Harry Belafonte and Marlon Brando and Roy Steger and many others. So that was a fantastic school of the actors who dominated the Hollywood also in the 50s, right after the Second War. And of course, after the Second War, the United States suffered from the McCarthy idiocy, and many foreigners who had found the place to live in the United States during the Second War, escaping from the torn by war Europe, like Piscator, Bertolt Brecht, and many others, Charlie Chaplin, for example, they had been accused by McCarthy of being essentially communist spies. And at that stage, Piscator had returned to Germany. And interesting, the same has been done by Bertolt Brecht. But Bertolt Brecht returned to the East Germany, and Piscator returned to the West Germany. And he was again a dominated person in the cultural world of Germany until he died in the 60s. All right, so we will be talking about the scientific relations of the Bertolt Brecht achievements in writing slightly later, but we will come to that. All right, so the Riemann changed the geometry and the way we humans were thinking about the geometry. And one of the results of that was that we started to think about what happens when the world we are trying to describe is higher dimensional than the 3-dimension. And sure enough, the lowest dimension higher than 3 is 4. And it turns out that the mathematical revolution, as well as the physical revolution of the mid of the 19th century, not only within the scientific circles. So I would like to say now a few things about the common perception of a 4-dimensional world. And an example of it is, this is a front page of a book written by a certain Anglican clergyman, Mr. Abbott, who had been signing many of his publications with SA.square. And the book is called A Flatland, a romance of many dimensions. And Abbott or Square, he was writing elementary texts about the higher mathematics for everybody to live. And he was writing them in the form of a romance, and that is a particular one. And the story is about the certain world which is two-dimensional. And there are creatures living in this two-dimensional world, and all of a sudden something shows up in that two-dimensional world. And well, the story goes on and it has lots of implication, but in fact, that's something what has shown in the two-dimensional world. It is a projection of a three-dimensional sphere. And this is the second page of that book. This is the preface to the second and revised edition from 1884. I happen to have that edition, so that is why I have also these things. And there is a prescription on top of it here, which says, "May I aspire yet higher and higher to the secrets of 4, 5, or even 6 dimensions, thereby contributing to the enlargement of the imagination and the possible development of the most rare and excellent gift of modesty among the superior race of solid humanity." In our words, in today's language, it will be much simple to say that what Abbott is saying is that the understanding of the fact that there is nothing much special about the three-dimensional geometry should be a common knowledge, because it allows us to enlarge our understanding of the surrounding universe. And when we open up the Copernicus Science Center, one of these items in our center, which is pretty unique in all over the world, is a robotic theater. There are robots playing as an actors. And our first show in 2012 was based on the Flatland story by Mr. Abbott. The play was written by one of the very distinguished Polish authors. And now we are, because it's a Stanisław Lem, famous Polish writer, science fiction writer, the robots are playing the play, which is based on the short novel by Stanisław Lem. So you can visit the center and see those robots. But there were many others who were busy with bringing this new achievement of mathematics to the common man, so to say. And that is a very interesting individual, Charles Hinton. Hinton was, and this is one of the front page of one of his books on the 4 dimensions, and that is a cover of the book which I have, which is a collection of Hinton writings about the 4-dimensional world. Hinton was a mathematician. He was a junior professor at several British universities, and he was so well included into this mathematical society of Great Britain at the time that he married a daughter of George Boole. Boole was a mathematician and logician who had formulated logic as a part, formal logic as a part of mathematics. And we are today using a Boole algebra, and the Boole algebras are particularly important for those who have studied informatics. For this basic logical rules are important in setting up the operations of the modern computers. Hinton married the daughter of Boole, but unfortunately it was found that he already was married to another lady, and that was, and I believe it's still a crime in most of the countries, at least in Europe. And so in order to escape a persecution, he took his wife, Boole daughter, and also this other lady, and emigrated to the United States. And very quickly he made a scientific career in the United States. He became also a junior professor of mathematics at Princeton University, which at that time wasn't so famous as it is now. And very quickly he ran into troubles there. They ran into troubles that he has misappropriated the university funds for his own personal purpose. And but he also had made a technical discovery. He built up a machine to throw the baseball balls. And this is a trainer for those who play a baseball in the United States. As you know, this is one of the most important games there. And it shoots, it's not the trivial, because the machine must shoot the ball towards the batsman in a well-defined solid angle. It's not allowed to throw the ball in an arbitrary way. And today, if you watch the baseball games, you see that the judge who is standing right behind the batsman and the catcher is wearing a particular helmet, which has a special optical device which allowed him to establish whether the pitcher throw the ball in a proper channel. But so he built the machine, and its modernized version are being still used today. So he makes lots of money on that sell of those equipment, and managed to solve the financial problem. But the major contribution of Charles Hinton was that simultaneously, before I will go on what was the contribution, what was the achievement of Hinton, let me mention another contributor to the popularization of a four-dimensional geometry for common man. This was a French engineer, a military engineer, Esprit Jouffret, who had written a book about the geometry of four dimensions, which was full of drawings. This is a copy of one of those drawings, which were projections of a four-dimensional objects on a two-dimensional plane. We will come back to the Jouffret book later on when we will be discussing paintings of Pablo Picasso. But the major contribution of Hinton was the way he showed us how we, the three-dimensional creatures, can see or envisage the four-dimensional object, and he took a simplest possible object, which in our three-dimensional world is called the cube. So you see there is a geometrical picture of a cube on the left of the view, which is anyway a two-dimensional illusion of a three-dimensional object. And that is because our brain is capable of that trick. We can, looking at this two-dimensional illusion, immediately envisage a three-dimensional cube, so to say, hanging in space before us. But there is another way of showing us a three-dimensional cube, and that is what is shown on the right side of that slide. Namely, this is a network. There is this 6 walls of the square drawn in a proper way on the plane, and there is a prescription. The prescription is shown with these little additions to the squares here and here and here. And these additions tell us how we can take now this two-dimensional object and glue the edges following that prescription. And that is the instruction that what we do this way will be a three-dimensional cube. And actually that what will happen. If we will take a piece of paper and do this drawing and cut it out and then they glue, we will have a three-dimensional cube in our hands. And of course, this is possible to do the same things for many other three-dimensional objects. And for example, this is another Platonic body, icosahedra. Icosahedra is a body which has a 5-fold symmetry. And those of you who studied the solid state physics knew that there is a problem with the 5-fold symmetry because the objects with the 5-fold symmetry axis cannot fill periodically a three-dimensional space. So therefore, there is a mathematical proof. The only mistake in this famous book, series of books by Lev Landau, which is a mathematical mistake because it's a mathematical proof that the 5-fold symmetry axis does not allow for a periodic covering of the three-dimensional space, but the icosahedra has a 5-fold symmetry, and this is this other way of, if we will take out of the piece of paper that drawing and fold together properly, we will get the three-dimensional icosahedra in our hands. Why I mention icosahedra? Because as you can easily count how many vertices it has. So if you put a real atom into the vertex of each of those vertices, and also in the middle of the icosahedra, you will have a cluster of physical atoms which are the same as in the building block of many real crystals in the world, FCC crystal, face center cubic crystal. However, the energy of that structure, the interaction energy between those atoms sitting in these vertices for icosahedra is slightly less than the energy for the FCC cube. And that means that if you have a finite number of atoms, and that you can prove exactly, the lowest energy state of them will be something like icosahedras, not FCC. So how come that there are no icosahedral-like crystals and there are face center cubic crystals everywhere? And that was a mystery until 80s when Danny Shechtman, following suggestion by John Kahn, had shown us how to create the icosahedral-based crystals. Well, because they cannot be filling up infinite space, they are not called crystals, but they are called the quasi-crystals. But they play an enormous role in the physics. And this is, for example, a picture of what comes out from a simulation on a computer of the 13 atoms of a copper or a gold, and I'm sorry, silver. And this is what you see is the minimum construction. And the icosahedras play the important role in the still not completed, in some sense, science, which is a science of crystallization. All right, so let's go back to the cube. We know how to produce the description of a three-dimensional cube on a two-dimensional plane. And this is here in the middle, you see the cube. And if you look at the walls of that cube, you see these planes, all right? And that is shown here. So these planes, then they can be rearranged to form that object. And when we glue it together, we will get a three-dimensional cube. Now imagine a four-dimensional cube. What is that object? It is very simple to write its mathematical definition. In a four dimension, the axis, there are four axes, as in our space we have three axes: width, length, and height. There is the fourth one, and a cube is a set of points in the four-dimensional space where the values of those four coordinates are less than one, and of course positive. So it's very difficult. There is no problem with writing a mathematical formula, but how you can envisage that structure or gain some information or some feelings, what are the geometrical properties of that hypercube? That hypercube was called by Hinton a tesseract. And what you see on the right is a result of this construction, but done for a four-dimension cube. For three-dimension cube, the projection of a wall is a square. It's a two-dimensional object. But if I have a four-dimensional cube, then its wall has three dimensions. So what you see here is a projection on a two-dimensional piece of paper of that three-dimensional object, which will be the wall of a four-dimensional cube. On the next slide, I show you something which probably is impossible for you to appreciate in watching the computer screen. It is so-called anaglyph picture. There are two drawings, and on top of each of those drawings, there is a white point. If you will be watching that picture, focusing your left eye on the left white point, and your right eye on the right point, white point, and you try to look at it and relax the muscles of your eyeballs as much as possible. Allow them to drift completely. Then after a certain time, these two pictures of on the left and right, this bluish picture, they should somehow, you will get the impression that they become a three-dimensional object hanging in the front of us. So that is the wall of a four-dimensional tesseract. So we can imagine this four-dimensional world, and the same way as, if I go back, if I can go back, and here there is a description of how to reconstruct, how we have to glue them in a four-dimensional space in order to get that object which is called the tesseract. So although we cannot see the four-dimension objects directly, but we can see two dimensions and the three dimensions projections of the pieces of that objects in our usual world. And that is something which plays the role in art. You might have heard about the famous painter Salvador Dali. And what you see on the right is one of the most famous paintings by Salvador Dali from 1954. It actually is called Hypercube. And this is a crucifixion on a cross, which is precisely that projection of a hypercube world. And the original painting is the Metropolitan Museum in New York. And on the left, there is a photograph of the Salvador Dali holding a real three-dimensional sculpture, which is the wall of the hypercube. So the four-dimension geometry appears in the art and has been used by the artist. That's not only this is the most famous one of those. But that is another projection of the tesseract into the three-dimensional world. And that is what you see here is the Grand Arch de la Défense in Paris. So if you will be next time in Paris, take a subway, go to Défense and look at this, and you can appreciate the fact that architects have been clever enough to took a piece of one of the other projections, not that one which I have shown you. It's so complicated that you wouldn't, it has to be considered in greater detail for many, many hours to understand why this is a three-dimensional wall. It's a piece of a particular projection of a tesseract into the three-dimensional world. But anyway, it's also used in the architecture. So this shows that the mathematical concept, which has come to our understanding through the habilitation work of Bernard Riemann, had also influenced the art. So it's another example that the artist, by making that picture with this painting which hangs in the Metropolitan Museum, could set some precisely the same information that we can do with the mathematics. And I'm unfortunately almost sure that most of the people who met and watch that painting have no idea that this curiously looking cross in the crucifixion painting is actually related to the four dimensions. I would like to show you something here, which will be a short movie. This is a movie about the hypercube. It's a kind of a thriller, and detective story, and that is only the trailer of it, which is available at the YouTube. So let's have a moment of why that has not. I'm sorry. This is always a problem with playing. Okay. Can you hear it?
Yes.
Yes.
The first cube was a formula for death. Unless you cracked the code.
These numbers are primed and the room is trapped.
But now,
Anyone here?
terror has a new dimension.
So does anyone remember how we got here? This isn't a game.
The store has rules. In this place, sleep defies reason.
The realities are starting to collapse.
Time has no meanings.
This is just an optical illusion or something?
In reality, nothing gets you. The fun's just beginning.
It's only a matter of time.
You're definitely not alone.
You stop here.
To hypercube. There are no rules.
I think you enjoy it, and I was unable to find the available full version of that movie on the internet, but I admit I'm not particularly skillful in searching the internet, so perhaps you will be having a more success if you will try. But when you were listening to this trailer, you might have heard the story about the time. And kindly remember that, because the time and a four-dimensional world will become important in our discussion in pretty soon. So, but it is not the only way the science, the knowledge of geometry and mathematics penetrated the art in the 19th century. So we start now a short discussion of a relation between this direction in the art, which is called Impressionism, and geometry. And what you see on that picture is on the slide is a painting by Edouard Manet, which is the Luncheon on the Grass, which is, this painting is considered to be the beginning of the revolution in the painting in the 19th century, which starts in France, which is called the Impressionism. We already have seen the autoportrait of Paul Gauguin at the first lecture, but that is this picture. Why I'm showing you that picture? Well, everybody knows it basically. But what is important about that movie, about its textual information, is that you have several individuals on that picture. There's a group of individuals, so to say, in a front, and there is this fourth person in the middle, so-called batting giant. Well, if you look at this painting very carefully, particularly on the eyes of those individuals, you will be able to see that is probably impossible from the computer screen, I agree, that these characters and the picture is, this whole painting is painted using not one point of a perspective. So this is not a one perspective in the Brunelleschi experiment, but there are three different points of perspective. For those group of individuals, that individual and the batting giant. And this is why if you will try to interpret this picture, this painting, as just drawn with the one perspective, you will not truly see that it's correct, because the dimension of a batting giant does not fit the perspective if these two groups of people are also on that picture. So the Impressionists were playing with using on their pictures not only different techniques of painting, but also we show it, for example, on the painting of Van Gogh, but they also play with the geometry. And this is another example. This is another painting by Manet, The Mirror. It's a bar in Folies Bergère. There is a person of that girl in a bar, the barrel girl, and behind her, there is a mirror. And the reflection in the mirror is that part of the room in which we are sitting. And these two sides are painted as being seen from a different point of a perspective. So this is also an example of a painting in which this game of perspective was used by Manet. But the most important and a curious example is the world of Paul Cézanne. Paul Cézanne, this is a picture of Paul Cézanne, and he made lots of those pictures. This is a one painting which is called Still Life with Basket, painted in 1895. You can see the Museum d'Orsay in Paris. The Museum d'Orsay is a former railroad station. That is something you should keep in mind. And this is the picture, Still Life with the Basket. Well, let's watch it for a second. And if you will carefully analyze that picture, you will find out, and this is analysis done by Early Lauren back in the 43, and this diagram shows the four observers who are, and the line shows what part of the picture of a Cézanne has been painted from a perspective point of those four observers. I consider this drawing to be a remarkable way. That was done in the 43, where there were no computer graphics. There were no vector algorithms which allow to decompose the picture in a various geometrical way. That has been all done by the compasses and rulers and so forth. So that is a remarkable piece of work, and also piece of art. Well, why it is so important? Because what you see on the right is base of the something we use in everyday life nowadays, which is called the GPS navigation. As you know, there are these satellites which sends the radio signals to our cell phones, and that's why we can travel easily using Google Maps or something. And the lowest number of a satellites which is needed to have to locate the object in a three-dimensional world we live in is 4. Well, in practice, there are much more satellites, and there are much more satellites, and the accuracy of the picture is so great because we have many satellites, and we also have a superb atomic clocks inside of those satellites, which allow us to build up the algorithms for GPS, which includes the general relativity theory information. But the lowest number mathematically, if we will have a superb precision clocks and so forth, the lowest number which is necessary is 4. And the 4 satellites allow us to make a whole picture of the world around us. Well, somehow the genius of Cézanne was that he was painting his still life with basket using those 4 quotation mark satellites, those 4 observers and their perspective, and created this beautiful picture. So we have the Cézanne Impressionism, and I told you that you should pay attention to this mentioning of a time on the trailer of a movie Hypercube 2. So we start now another part of our discussion, which follows the geometrical things, which I call time and motion. And what you see here is a picture by René Magritte from 1935, which is now in the Art Institute of Chicago. And that is a picture which combines a notion of time, a clock, and the notion of a motion, and the notion of motion. This steam engine emerging out of the fireplace. Well, as you might know or might remember, what Einstein uses as models of various experiments to broaden us the concept of special theory of relativity were the railroads, the trains moving. So that is why I choose that picture to begin our discussion of a time and motion. In the middle of the 19th century, people were extremely excited about the concept of a time and motion. And that was related to the railroads. This is a picture which I already have shown you and warned that it will appear often. This is a lightning express leaving the junction, this metallographic by the Curie and Ives. And people were extremely, they start thinking about I'm sorry, I have to switch off my phone because it's ringing. And the picture of the railroads have changed the role the time played in our daily life. Previously, the fact that there is a time difference between Warsaw and Paris or Warsaw and New York was not really playing any practical role in our life, because a trip from Warsaw to New York took so long when Julian Ursyn Niemcewicz or his wife were traveling to Boston and back. it took them so long that they didn't feel the change of the time. There was no concept of a jet lag, and there was no need of using a special pills to overcome it. And this is a famous picture of a Gare Saint-Lazare, railroad station Saint-Lazare, by one of the French Impressionists, the other Impressionist, Claude Monet. The luncheon on the grass is Monet. And this is a picture made in 1877. And that picture also hangs in Paris on the Gare d'Orsay. And this is an example of the fascination of the people there with the motion, which is the travel. For them was a travel by the trains, and the time it played. The time and its adjustment was a problem which has been extremely important for, of course, science, but not only. So this is a short history. It was 1687 when Newton, writing a Principia, used the concept of absolute time, a fabric of the universe which runs independently of whatever happens, and we can mark each event in the past and future of whatever happens in the universe using that absolute time which runs in space. This concept of the time is slightly differently phrased in the famous works by Immanuel Kant, particularly in a critique of pure reason. If you will ever try to read a book of philosophy, and don't start with the modern philosophy, start by reading Immanuel Kant. And then Kant, of course, was not a specialist in traveling. He never traveled out of Königsberg. He only once tried to travel, and he traveled several miles out of Königsberg and returned. But the problem was that the railroads have changed the use of time. And eventually, I just realized that I make a mistake. These 2 points have to be exchanged. But the fact that the trains were running along distances sufficiently fast so people have feel the difference of a geographic time had contributed to the shared history of a railroad time. That was particularly important in the United States, because in the end of the 19th century, 80s of the 19th century, when you took the train from, say, Philadelphia to San Francisco, which was already possible, there was no single company which operated the whole line. There was, I believe, 18 companies which ran pieces of those railroads, and they were located in different places. And each of those companies used the time, geographic time of their headquarters. So the passenger who was boarding the train in Philadelphia, and going to the San Francisco, and if he wanted to be at each place in which place he visited on his way, on time of a company which operated that piece of railroad, he will have to reset his watch at least 18 times. There was a complete mess with what was meant by the what time on the railroads. In France, this was solved in a very peculiar way. There were, on the railroads in France, there were two times. It was a railroad time and the railroad station time. And a railroad time was a time of Paris, of the city of Paris, and this was a time in which the schedules of trains for the operators of the trains was written and used. But on each railroad station, there was a railroad station time, which was shifted by something like 5 minutes as with relation to the railroad station, to the railroad time, in order to allow a passenger a luxury of being slightly late for their train. And there were any other problems with the time, and eventually people got convinced that they have to rearrange the structure of a time, and there was the famous 1884 Meridian Conference in Washington, D.C., which set up a structure of how we count the time on the surface of the earth, which basically is the same as we are now using. The people who were extremely pushing for the introduction of some rules of how to calculate the times on the railroads were military. And chief of the Kaiser staff, Graf von Moltke, realized that he will be unable to run a countrywide mobilization of his army, for the army had to be mobilized in 19th century essentially by railroads. And he wouldn't know at what time, which train is where, because they were all operating on the local times of their companies. So the introduction of a common structure of a life was important. And this is basically the Washington, D.C. construction of the time from the 19th century. Well, the point was so important that one of the greatest mathematicians of the second half of the 19th century, Henri Poincaré, had started to worry about how to incorporate a change of time and structure of the time into the description of a mechanical world. Henri Poincaré was a mathematician who contributed. If you will now look at the modern mathematics of the topological algebra and many others, at the beginning of those fields, there is most probably always something written in the 19th century or the beginning of the 20th century by Henri Poincaré. He also was the author of the important books which were fundamental reading books for most of the educated people in the 19th century. And this is a copy of one of the most important books by Henri Poincaré, Science and Method. the book which set up the way we are thinking about the using science as a method, not only for science per se, but also for our life. Poincaré had been the author of the first concept of including the time as the same notion, not as an absolute something, as in Newton geometry. He was interesting individual by himself. He was a nephew of an important politician in France at the time. His nephew was a minister of foreign affairs and eventually a president of the Republic. So Henri Poincaré had been invited to the many parties, official parties, and he always was coming there with his 3 daughters. And one of these probably male chauvinist stories about the Poincaré and his daughters was that when he was on this party, he used to introduce his daughters as Mademoiselle Alpha, Beta, Gamma Poincaré. But the Poincaré has been important in this development of a theory. And his books have conveyed the mathematical and physical theories to the intellectually awakened individuals in the society in that time. So let me show you the picture of Herbert Wells, the founding father of a science fiction stories. And as you know, he had written many interesting books, but one of his books, written first published in 1895, was a book about a time machine. It's a time traveler who is a hero of that book. And let me show you a fragment from that book, which I choose for our purpose. Well, it's pretty long. It's a discussion with his friends of a time traveler, but let's look at the red lines. There are really 4 dimensions, 3 which we call the 3 planes of space, and the 4th time. But some foolish people have got hold of the wrong side of the idea. You have all heard what they will have to say about his 4th dimension, and have even tried to construct the 4-dimension geometry. Professor Simon Newcomb was expounding this to the New York Mathematical Society only a month or so ago. So the concept of the 4-dimension geometry and the relation of a time and space has become not only a subject in the popular science books like Mr. Abbott or Mr. Hinton, but they become a part of a literature. And the 4-dimensional space and time is this geometrical construction in which the travels in time by the time traveler in the Wells book is happening. This is another very famous book by Wells, The Invisible Man. And that is a picture from the movie made in 1933, the first movie, Invisible Man, with Gloria Stewart and Claude Rains. And this is a quotation from that book. And I hardly worked and thought about the matter 6 months before light came through one of the meshes suddenly blinding. I found a general principle of a pigments and refraction, a formula, a geometric expression involving 4 dimensions. Fools, common men, even common mathematicians do not know anything of what some general expression may mean to the student of a molecular physics. Even he tries to convince the readers the information that perhaps even the chemistry is actually correct to describe in the four-dimensional world. But that is not a popular science book. It's a novel. He wants to sell the novels, and people were buying it. But it's not only the Wells who was writing the novels, scientific novels. By the way, one of the novels by Wells is called The Island of Dr. Moreau. This is a book. This is a book on which, base of which, Frankenhammer had made a movie in the at the beginning of the 20th century, starring Marlon Brando as Dr. Moreau. Dr. Moreau is an individual who lives on the remote island somewhere on the Pacific Ocean, where he performs unhuman experiments by cloning humans with animals. And I remember vividly that when ship Dolly was cloned and the world learned that the cloning of the animals is possible, that day when that became a news in the television, I was in Edmonton in Canada watching the evening news. And after that, I was watching I brought in from the one of these places where it lent the films of the cassette at the time, a film, the Frankenhammer film, the Island of Dr. Moreau. And I was watching that movie and I stopped it to watch the news. And I stopped watching the movie about the cloning the humans with the animals when the news was that the Dolly was alive and well and cloned. So that was a quite exciting event. But let me come back now to the main subject. There were popular books and there were science fiction books, and there were plenty of these modern notions of science penetrating the art. And also we discuss it in the art of painting. But this is Joseph Conrad, one of the main authors of the Marinistic literature of the world, and our compatriot, Józef Korzeniowski. And he had written, of course, many books, but the one book Conrad wrote with another individual with the name Fort Haffe, and the book is called Inheritors. It was published in 1901, and here is a quotation for it. "Listen," she said, after uttered some sounds. "I felt a kind of unholy emotion. I had come like a suddenly harsh and intense gust of wind through the breathless day. What, I cried. I said I inhabit the fourth dimension." The very sinister characters in that book are they said they have lived in the fourth dimension. And I come from a fourth dimension. I heard the nature here and so forth. So even the authors of a very serious literature had been trying to use this new concept of science in their artistic work. But that's not the only way. This is another book, a truly very famous. This Inheritors book is a marginal. in the artistic contribution of Conrad. But one of his main books is a book called The Secret Agent. And the story is about a certain gentleman named Verloc, who is an agent he's a spy for someone, for some country. The name of that country is never mentioned, but he spends lots of time talking to a person who runs him, who is a consul Vladimir, and that he is a representative of a Tsar Okhrana in England. Tsar Okhrana was a secret police predecessor of KGB, and Vladimir is ordering Verloc to perform a terroristic attack in England, but they discuss it, and this is what Vladimir is saying. The demonstration might be against learning science, but not every science will do. The attack must have all the shocking senselessness of a gratuitous blasphemy. Since bombs are your means of expression, it would be really telling if one can throw a bomb into pure mathematics. And what Verloc is doing, he prepared a bomb attack on something which is a statue of science on the British Islands. It's a Greenwich observatory through which the zero meridian is passing. So he is attempting to throw the bomb into the mathematics, into the basic science. And that is another example that a science was a part of an everyday life of at least the intellectual part of society in the 19th century. The Verloc is actually not, well, the terrorist attack was supposed to be performed by a chosen mentally impaired brother of his companion, and that doesn't happen. That individual dies, explodes the bomb before he reached the Greenwich. And this is a very, very interesting book. I suggest you read it if you have some free time. All right. And I would like to finish today's part of our discussion by mentioning you another contribution to our discussion, how science and art are interrelated in the 19th century and at the beginning of the 20th century. And that is a book, a trilogy by a Polish writer, Jerzy Żuławski, who lived from 1874 to 19. This is his picture. And that trilogy has, of course, 3 books. The one is on a silver globe. The second was the Victor. And the third one, on which I am going to talk more, is called Old Earth. The story is about the travel to the moon. We will be talking about the book of Jules Verne in what follows, but this idea of going on to that globe which hangs on top of us and which we call the moon was with humans since much early. The French author Cyrano de Bergerac had written a book about it. Jules Verne had wrote a book about it. And Jerzy Żuławski had wrote a book about it. The story starts with the excursion to the moon, which happens by means of a projectile fired towards the moon from a gun. That was the idea which was in the 19th century considered to be a scientifically sound. And even Verne knew that the gun must be very long, and therefore he had placed it perpendicular to the Earth's surface in the Congo River. And next to the Congo River. And this super gun fires to the moon a group of individuals. One of them is a female, and they land with a crash. And husband of the ladies get killed, and that, of course, creates a problem between two other men in this team. And anyway, they travel over the moon, and they find out that on the other side of the moon, which is not visible from our side, there is a life. I'm not going to abbreviate these two books, but this life is run by, there are some kind of humans. They are, of course, smaller because of the gravity and so forth, but they have their own religion. They have own clergy. And finally, one of those who arrive from the Earth lives very long, and he's the old man. And this is a story. Żuławski writes the story how the new religion is being implemented on the surface of the moon. And when you read it, you can easily find out that the main lines of that story are very similar to for example, Frank Herbert Dune. But the third volume is Old Earth, is a story on the Earth which happened after this trip to the moon, and describes a society which looks very similar to our now society, is completely penetrated by the scientific discoveries, by the communication and so forth, the transfer of the information. And then those priests of all religion from the moon says one of those the people traveling to moon brought with themselves the other possibility of coming back. So they get possession of that ship, and they travel back to the Earth, and they bring a complete havoc to the world civilization, and it ends up with the counter-intellectual revolution. What Żuławski was afraid that the tremendous expand of science, which he has already seen in the 19th century, may not be accepted by a considerable part of humanity, something which is happening right now. And he dared to write what can be a consequence of it. And I copy for you an announcement of a new government of the Earth. Citizen, We no longer need the wise men. It's enough for us what we have gained so far. And there are 6 points. Today, the Society of Scholars, known as the Brothers Knowing the Existence, will be dissolved. All salaries previously paid to scholars are abolished, leaving them free to earn by hand if they wish to live. Likewise, all establishments, so-called pure science and infertile research devoted to fertility are abolished, leaving only institutes of a social benefit and economical values. In the future, it is forbidden to maintain private laboratories and under heavy penalties and publish works that would not be directly recognized as useful by a separate censorship commission in the manuscript. By keeping the existing vocation schools in force and in full pay, all higher schools, the so-called philosophical or general, and above all, at the expenses of the government, the school of the sages, that is a school playing important part in the story, are closed once and for all. In order to make it impossible to circumvent the above ordinance, all private teaching is strictly forbidden, no matter what presented it may be. In other words, the science is stopped. And that is the book by Jerzy Żuławski. And essentially, 8 or 9 years after the book has been printed, in the other part of the world, in the United States, in Pittsburgh, a judge sentencing American engineer Lee DeForest, a person who invented a pentode, electronic lamp pentode with 5 electrodes, which makes possible building up a commercial radios. He sentenced him, and he says that sure enough, he must have been lying to the sponsor that he can produce some new discoveries needed for the humankind, for we already have everything we knew, and there is no reason why we should try to find out anything new which we can use in our daily life. Żuławski was an extremely, the books are fantastic, and his grandson, Polish movie director Andrzej Żuławski, make a movie, which is a screen version of the first volume of the Silver Globe trilogy, namely on the Silver Globe. That is a very curious movie. But this is another example how science was deeply interwoven into the daily intellectual life of a society in the 19th century. And now, already now, you can compare it with what happens now. Well, thanks a lot, and we see each other next week. And I don't know what had happened with this recording. We will be thinking about, we will be thinking about that in the future. I don't know why it hasn't been recorded. So thanks for being with me, and let's see us next week. Bye-bye.
Thank you.
Thank you.